Hey guys, today we are going to solve this problem, reachability and tree. So it was a problem of educational code forces round 180 rated for div 2. So let's start. So let's read the problem. It says that we have been given two distinct vertices u and v in a directed graph, and we call ordered pair of two nodes u v good if there exists a path from vertex u to vertex v along the edges of the graph. And we are given an undirected tree with n vertices and n minus 1 edges, and we have to determine if it's possible to assign a direction to each edge so that the number of good pairs in the tree is exactly n. And if it is possible, you have to print the directions of the edges, otherwise you have to print no. Okay, so let me just explain you the problem here. Okay, so what you are given is you are given a tree, so or you can call it a graph as well, no issues. So let's suppose this is a graph given to me. Okay, 1 2 3 4 5 6, and the node values is always unique. It has been said in the problem. So here we can see that there are six nodes and five edges. Okay, now initially you are given an undirected graph. You have to give directions to these edges, and you have to make sure that the number of good pairs is exactly n. Now, how is a good pair defined in this problem? It basically says that let's suppose that there is a node u and there is a node v, and if there is a direct edge existing between these two nodes, then they form a good pair. But it's not necessary that there should be direct edge. There can be some nodes also in this path. So if there are, let's suppose, two nodes in between these two nodes, and u is going to this node and then to this node and then to this node, then here also u and v are forming good pairs. So here the number of good pairs are u to v. This is one good pair. Another good pair would be this one. Okay, so let's call it as x node and this as y node. So u and x also form a good pair. Similarly, your x and y also form a good pair. Y and v also form a good pair. X and v also form a good pair, and u and y also form a good pair. So there can be multiple good pairs here, right? So this is what is defined as a good pair in this problem. Now what you need to do is you need to give edges, you need to give directions to these edges such that there are exactly n number of good pairs. Okay, this is the problem. So now I am pretty sure that you might have tried to solve this problem, and even if you have not tried it, I would strongly recommend you to first give it a try, because that will help you understand the solution in a better way, and you might be able to solve it on your own as well. So this is for those people who have tried this problem and they just want a hint. So the hint number one is that there is only one solution that exists in this problem. That is, there is just one condition that is required to be present in the given graph. If that condition is satisfied, the answer will always exist. But if that condition is not satisfied, the answer will never exist. This is the first hint. Okay, now let me just give you an example. Let's suppose that you are given this graph 1 2 and 3. Okay, let me just erase this old one. So you are given this simple graph 1 2 3. Okay, three nodes and two edges. Now if I say that I give a direction to these edges, let's suppose I give this and this, then in this case how many good pairs are there? 1 and 2. So there are only two good pairs, right? Only two good pairs. But what we want is, we want three good pairs. How can we make it as three good pairs? So let's try to change the direction. Let's suppose I remove this and I reverse this direction and I make it in this direction. Okay, now how many good pairs do I have? 1 2, 2 3, and 1 3 as well. So now I have three good pairs, and this will be your hint 2. This is the only condition that is required to be present in the given graph for the answer to exist. If this condition is not satisfied, the answer will never exist. Now let's talk about what condition am I talking about. So for the people who have already tried this problem, just take this as an example, as a hint, and try to solve it. Now I'll tell you what condition is required, what exactly I'm talking about. See, first of all, let's forget about this condition. I will explain you one thing. Let's suppose that I am given this graph let's suppose 3 2 1 and 5 4, and let's suppose 6 and 7, and let's suppose 8 and 9. Yeah, suppose this is a graph given to you. Okay, so there are how many? 9 nodes are there, and there should be 8 edges. Yeah, there are 8 edges. Okay, now if I tell you, one thing that you have to note is that if you are given n nodes and n minus 1 edges, then you can always create n minus 1 good pairs. Always, it's always possible. How is it possible? I'll tell you. See, let's just start from 3. Okay, now what I'll do is I'll make outgoing edges from 3, all the outgoing edges. Now I go to 2, there is an incoming edge, right? So I'll make all the edges to 2 as incoming. Now I go to 4, there is an incoming edge, so I'll make it all the remaining edges as incoming. Now from 1 we have one outgoing edge, so we will make all the edges from 1 as outgoing. Okay, now I have given direction to all the edges, right? No issues. Yeah, so now here you can see that let's count the number of good pairs in this problem. So it's 1, then it's 2, then it's 3, then it's 4, then 5, then 6, then 7, and then 8. Now there are no more good pairs. There are exactly 8 number of good pairs, that is n minus 1 number of good pairs. So can you observe something here? I'll just erase this. Can you observe something? Yeah, the observation is very simple. The observation says that first of all you have one node, and from this node you have all the edges as outgoing. Then at the next level you have nodes for which all the edges are incoming. Now again for the next level, that is if I talk about the BFS traversal, for the next level all the nodes have outgoing edges. So this and the remaining, the next level has again incoming edges, right? So you can see here that we have alternate outgoing and incoming edges. So one conclusion number 1 is that if we are given a tree or a graph of n nodes and n minus 1 edges, and if into that graph we assign alternate incoming and outgoing edges, we will always have exactly n minus 1 number of good pairs. So if you do this, that is if you assign alternate outgoing and incoming edges, you will always have n minus 1 number of good pairs. Okay, fine. But in the problem it has been asked that we have to create exactly n number of good pairs, not more than that, not less than that, right? So that simply means that you have to increase one good pair anyhow, right? Anyhow you have to increase the number of good pairs by 1, and then you will be good to go. How can we do that? I'll just write the earlier problem that I took as an example. We had 1, we had 2, and then we had 3. And I said that if you give the directions in this way, you will have n number of good pairs. This will be 1, 2, and this one will also be there, 3, right? So if you can implement this in this given graph, you will be able to create exactly n number of good pairs. So can I compare these 3 nodes with these 3 nodes 1 2 3? So let's assume that this is 1, this is 2, and this is 3, right? Now what I am saying is that from 1 you are going to 2, so 3 is going to 4, fine. Now if I reverse this edge, then I think I will be able to create n number of good pairs. Let's see. So first of all I'll erase these colors. Okay, now what I'm saying is that I'll just take this edge and I'll reverse it. So let's take this edge and reverse it. Okay, I've reversed this edge. Now let's count the number of good pairs. So you have 1, then you have 2, then you have 3, then 4, then 5, then you have 6, then 7, and then 8, and then you have 9. Now I cannot see no new number of good pairs, right? So you had to create 9 number of good pairs and you have created it already. So yeah, the answer exists and this is your answer. So now what is that condition that is required? Now I'm going to talk about that condition, the necessary condition for the answer to exist. And the condition is this. It's very simple. This is the condition that is required. This is the condition that is required. Okay, now let's talk about it. How do we prove that the solution will exist and why it will exist? So the condition is that we want at least one bridging node. Okay, listen to me very carefully. What we want is for the answer to exist. That is, if we are required to create exactly n number of good pairs, there must be at least one bridging edge. One bridging node that must be present in the given graph. Then we can always create n number of good pairs. So that simply means that, let's suppose that there is a node given to you, this, and then there is a bridging node given to you, this, and there is another node given to you like this. Okay, now what you can do is you can always give the edges the direction in this way, from this node to this, and then from this node to this. So this will always give you one extra number of good pair. And what will be that extra number of good pair? This one. Because you already had this as good pair, this as good pair, and this one you will create an extra. And that is why you will get your answer. And what about the remaining edges? We have already made them bounded. That is, there will be exactly like we worked when we worked upon this graph, we made sure that there are exactly n minus 1 edges, and then we found that there is a bridging node here. So we reversed this edge and we found out our answer, right? So we do not need to worry about the remaining edges. Okay, we just need to reverse one edge and we will have exactly n number of good pairs. But still there is a very crucial point that is remaining that we will discuss here. Okay, so first of all, let's just make edges here. I'm not giving the numbers, or okay, I'll give the numbers and I'll tell you. Okay, so let's suppose this is it, and this is it. Okay, fine. So let's suppose that this is a graph given to me and I'm giving the numbers as 1, 2, 3, 4, 5, 6, 7, 8 and 9. And I'm saying that if there is a bridging node existing, then I can always say that my answer exists. Okay. Now let's just do that thing that we did earlier, that is give alternate incoming and outgoing edges. So for 1 it will be outgoing, for 2 it will be incoming, for 3 it's outgoing, 4 it's outgoing. Okay, now for 5 I will say outgoing, 5 outgoing, 6 incoming, right? So when we just give this alternate incoming and outgoing edges, we are always bound to have n minus 1 number of good pairs, and that is what we can see here: 1, 2, 3, 4, 5, 6, 7, 8. We have exactly n minus 1 number of good pairs. Now the question might arise, why do we have exactly n minus 1 number of good pairs? The answer is very simple, because we have made the edges as bounded. That is, when we go from any node u to v, we cannot move any further. That is, there is only one path that is existing between two nodes. And since there are n minus 1 edges, we have exactly n minus 1 number of good pairs. Okay, so yeah, that's it. So now what do we do is, here we are saying that we just need to reverse one edge, right? So if you remember, we had like 1, 2, 3. We need to create something like this. Okay, so here I can see that, let's suppose this is 1, assuming that this is as node 1, this as node 2, and this as node 3. I have to make this as the direction, right? So this simply means that I have to reverse this edge. So let's just reverse this edge. So what I'll do is I'll select this edge and I'll change the direction and I'll reverse it. Okay, so is this your final answer? No, this is not your final answer. You have to make some more changes. What are those changes? See, let's just count the number of good pairs. Okay, I just reversed the edge and now I'm counting the number of good pairs. So it will be 1. I'll draw this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You can see there are many number of good pairs. By just reversing this one edge, we cannot be sure that we will have exactly an n number of good pairs. We will have to do some more changes. And those changes are that you will have to reverse the remaining edges also. Why? I'll explain you. First of all, let's just reverse these edges as well. So I'll say that I'll reverse this one and I'll reverse this one as well, and I'll also reverse this one. So now I have reversed this edge, this edge, this edge, this edge. Okay, I have reversed these 4 edges. Now let's count the number of good pairs. So we have 1, 2, 3, 4, 5, 6, 7, 8 and 9. Yes, we got our answer. So did you observe something? Observation number 1 is that there must be a bridge node that must be present. And how do we define a bridge node? A bridge node simply means that it will have two nodes connected to it, one to the left and one to the right. Although it's not correct to say left and right, but still I'm just saying that you will have just 2 nodes connected to that one node. If this node is existing, you will always say that the answer exists. And the second point is, like if I talk about the steps. So first one, check if there is a bridge node present or not. If it is present, just record its location. And before this step, you need to do one thing. This is your step number 2. Your step number 1 is that give alternate incoming and outgoing edges to each node. Like in the BFS traversal, for the first node you will give all the outgoing edges, and for the other level you will give all the incoming edges. Then for the third level you will again give outgoing edges. So when you do this, you are always bound to get n minus 1 number of good pairs. Now the second step will be, so the first one will be to create exactly n minus 1 number of good pairs. And your second step would be to search for a bridge node. If there is a bridge node existing, you will say that the answer exists. Otherwise you will say the answer does not exist if this node is not existing. Now your third step is to reverse just one edge. One more thing, you could have reversed this edge as well. Although you reversed this edge, you could have reversed this edge as well. But here in this example, I reversed this edge. So now when I reverse this edge, the remaining edges, that is all the edges on this side, on one side of this bridge node, you will have to reverse those edges as well. Because if you don't do, you will have more than n number of you will have more than n number of good pairs. That is something that you do not want. So you will always make sure that whenever you are reversing one edge, all the edges before that node, or we can say that all the nodes connected to that node, you will also reverse their edges. And then you will say that yes, we have created n number of good pairs, exactly n number of good pairs. Okay, now let's talk about let's just take another example. Okay, and let's see how are we able to conclude that the answer will exist only if there is a bridging node, otherwise the answer will not. Let's see. So now what I'm doing is, I'm taking this exact same example. I'm removing the directions as of now. Okay, so let's just remove the directions. And what I'll do is, let's suppose I delete 7 from here, I give 7 here, and I delete 4 from here and I give 4 here. Now this is a graph where there is no bridging node. There is no bridging node, right? So let's just first of all give alternate outgoing and incoming edges. So I'll say that this is outgoing, this is incoming. Then for 5 you have outgoing, and for 6 you have incoming. So now you will count the number of good pairs. They will come out to be exactly 8, because we have 9 number of nodes, so there will be 8. Now we will search for a bridging node. Is there a bridging node? That is a node which is connected to just two nodes, exactly two nodes. No, I don't think, right? Because it's connected to 1, it's connected to 3, it's connected to 1, connected to 1, connected to 4, connected to 1, 3, 1, 1. Right? We do not have any node which is connected to exactly two nodes. So that simply means that the answer will not exist. But let's try to do the same thing that we did earlier. That is, we reversed this edge, assuming that, okay, so I'll just try to reverse this edge. Okay, what happens if I reverse this edge? There will be more number of good pairs that will be that will start to exist. It's like 1, 2, 3, 4, 5, 6, 7. So did you observe something? If there is a node which is having more edges, like more than two edges into it, there will always be more number of good pairs that will be created. So you do not want this edge here, you do not want this edge here, because if they will be present, you will always have extra number of good pairs. And even if you say that I do not give this, I reverse the direction, let's see what happens if we reverse this direction as well. What will happen if I reverse this direction? Then again you will have extra number of good pairs. This will be this, and then this will be this. Okay, these are extra number of good pairs that are being created. So that simply means that the answer will only exist if there is just one bridging edge, bridging node. What do you mean by a bridging node? A node that is connected to two nodes, okay, via two edges. If such a node is existing, we will say the answer always exists. And what do? We will say that, let's suppose there is some random graph given to you. Okay, some random graph given to you. We will always search for a node which is the bridging node, and it is connecting these two components of the graph, and we will call this as node B, this as node A, and this as node C. What we will say is that we will say that this edge, we will reverse it. If it is in this direction, we will make it in this direction, and if it is in this direction, we will make it in this direction. We will reverse this edge, and all the remaining edges of this portion, we will also reverse them, because we earlier saw here, right, we saw here that if we don't reverse these edges, we will have extra number of good pairs. So as to avoid this, we will reverse these edges as well, and this will remain as it is. This edge and all these edges here will remain as it is. Only these edges we will have to reverse them. Then we will have exactly n number of good pairs. Okay, so this is the simple logic of this problem. I hope you have understood it. And actually the implementation is not, I would say, tough, but yeah, it's little lengthy. But yeah, actually this problem was very interesting. So now I'll show you the code. Okay, so just a minute. Yeah, so this is your code. So first of all, I am inputting n, that is the number of edges. Now I'm creating a vector of pairs wherein I'll store the edges, and I'm also storing the adjacency matrix, the adjacency list of this graph, the given graph. So now I'm inputting n minus 1 number of edges. So these are the nodes u and v. So I'm storing it in the edges vector and as well as in the adjacency list. Now I'm creating another vector which is defining the edge type of a particular node. So if it is 1, that simply means outgoing edge, and if it is minus 1, that simply means incoming edge. Now this portion is simple BFS traversal of the graph, and I'm simply assigning alternate outgoing and incoming edges to the nodes. Okay, it's very simple. You can just see that I have created a queue, and I always say that I start the BFS traversal from 1, and I say that the edge type of this node will be alternate 1 and minus 1. Okay, yeah, so it's very simple. So just the BFS traversal of the graph. So now once I've assigned these directions, what I do is I search for two nodes A and B. What are those two nodes A and B? B will be your bridging node, and your A will be any node which is attached to B. That is, you can take, like I am saying that this is your node B, and this can be your node A, or this can be your node A. doesn't matter, you can take any of them. Okay, so yeah, that's it. And now I created a quick check function to get the values of a and b. So this is my check function, and here what I'm saying is that I am going to each node and I'm checking the adjacent nodes of that node, and if the adjacency list size of that adjacent node is equals to 2, then I'm saying that the node will be my a and my adjacent node will be b. So essentially what I'm saying is that I'll go to each node and I'll say that if for a particular node there is an adjacent node, there is an adjacent node that is having two elements in its adjacency list, that simply means that the adjacent node will be my bridge node and my current node will be my node a, which I'm calling here as a. Okay, this can be a and b, or this can be a and b, whatever you take, right? So yeah, this is what I'm saying, and then you return. And if such a node will never exist, the a and b value will never change and they will remain as -1. So I'm saying that if my a is equals to -1, see out no. That simply means that no bridge node was existing, and that is why I have returned no. Now what I do is that so from this point is again the BFS traversal, and what I'm doing is that I am reversing all the edges of this portion. So I earlier said that you will have to reverse this edge and all these edges also, right? All these edges also you will have to reverse. So that is what I'm doing here, the simple BFS traversal starting from node A, and I'm reversing all the edges. And I'm also just creating a bool reversed hash so that I always store that the what are those edges which have been reversed. That is what I'm saying. Okay, now after that it's very simple. I am going to each of the edges and I'm saying that if it is a and b or b and a, then always make sure that the node is reversed. So this is basically reversing the edge between a and b. Okay, yeah, so I'm not saying that the implementation is very like the best implementation. I know the implementation might become better, but yeah, at least it's very intuitive and it's very clear, right? So yeah, that's it. So this part is just for reversing the edge between a and b, and this part simply says that if there is -1, then that simply means that the v node should always appear after u. So essentially what I'm saying is that, let's suppose you have two nodes u and v, and u has an outgoing edge at -1, v has an incoming edge. That simply means that you will always write the pairs as u and v, not v and u. So if v and u is present and v is having a -1, just swap these values. That is what I'm saying here in this part. Yeah, and then after that I'm saying see out yes, and then I'm printing the edges. That is very simple, right? So this is an example, so let's just try to run it and let's see what answer do I get. Okay, it's taking a lot of time. Yeah, this is the answer that we got. So let's just paste this graph here and also paste the answer here, right? Yeah, so we were given this graph 1 4 1 4 1 5 1 6. I'll draw it here. Yeah, 1 2 1 2, then 2 3, okay, then 7 3, okay, then 3 8, okay, and 3 9. And I'm saying the answer is existing and the directions are 4 1, okay, 5 1, okay, 6 1, okay, 2 1, okay, 3 2, okay, 3 7, and 3 9, and 3 8. So yeah, that is what you can see here, that there are exactly n number of good pairs, right? This is 1, this is 2, then this is 3, and then 4 5 6 7 8 9, exactly n number of good pairs, right? One more important point. So what we did essentially was, we said that initially, I'll just simulate the code here. So what I'm saying is, start from 1 and give alternate outgoing and incoming edges. So for 1 you will give 1, so 1 means outgoing edges. So for 4 you will give -1, 6 you will give -1, 5 you will give -1, and 2 you will give -1, and 3 you will give 1, 9 you will give -1, 7 -1, and 8 also as -1. So these are the type of the edges that are present in the node, that is outgoing or incoming. Now after that, what do we say? After this we say that find out a bridge node. So yeah, this is the bridge node, and then we are saying that just reverse the direction. So let's suppose that no yeah, we are saying that find out a bridge node. So this is the bridge node, and we are saying that take any part of the left or the right part of the bridge node and reverse all the nodes. So I'll take this and I'll reverse these parts. So if it's 1, I'll say -1. If it's -1, I'll say +1, -1 +1, -1 +1. Now when I'm printing the edges, I'll always make sure that if there is 1 2, then always the direction is reversed. So if it is having -1, that simply means that the edge was of 1 to 2 type. So we will say that if 1 2 is there in the pair, you always make it as 2 1. Okay, that is what is meant by reversing the node. So what we will do is, this was the edge list given to us. Okay, now before reversing them, the edges were like this. So now we will go to this, let's suppose 1 4. So 1 4, the node should be for 4 to 1, so we will swap it. So 1 4 will become 4 1. So 1 4 will become 4 1. Now we go to 1 5. So 1 5 we should be having 5 1, so we will again reverse it. So 1 5 will become 5 1, sorry 5 1. And then we go to 1 6. So again 6 is outgoing, so it should be 6 1. We will swap it. Now we have 1 2, and earlier we said that the node was existing like 1 2 2, so we will say 2 2 1. So we will also reverse it. So we will say that 1 2 will become 2 1, right? And then for 2 3, 2 3 is 3 2 2, so we will reverse it as well, 3 2. And then we will say 3 2 2, yeah. And then we will say 3 8, so 3 7, so 3 7, we will swap it. Then 3 8 will remain 3 8, right? And 3 9 will remain 3 9. Yeah, that's it. So this will be your final answer. Yeah, so that was it. I hope you have understood this problem, and the problem is actually very simple. You just had to observe one thing, that there is only one particular condition that is required to be satisfied, and that is this bridge node. If this bridge node is existing, what you will do is you will just reverse this edge. Okay, sorry, you will reverse just this one edge, this one, and all the remaining edges of this node. Okay, all the remaining edges of this node. Okay, you will reverse them and you will have your answer. So yeah, that is for today. I hope you understood this video, this problem, and if you have any doubts, you can ask it in the comment section. Yeah, that is it. Thank you.